In this video lesson, we're going to explore the properties of linear relations. This is important for Math 10 students because these ideas lay the basis for your next couple of math courses. And those next couple of math courses are going to expect that you know a lot about working with linear functions. As well, our next chapter of this course, Math 10, relies on linear-based skills. So this is where a lot of important ideas begin to grow. When we talk about linear kinds of patterns, we can see these in several different ways. In a graph, we see that whether or not the data is continuous, the points line up. They make a straight line, and so we call it linear. In the table of values, we have to look at what's going on in terms of the change. In this table of values, we see that the cost is increasing by 75 cents every time the number of extra toppings on the pizza increases by 1. This in the table gives us the same sort of straight line pattern if we plot the data, and so it's also a linear pattern. The formal way to talk about linear patterns is to say that the change in the ratio, or the fraction, of the dependent variable, or the y data, to the change in the independent variable, which is the same thing as the x data, is constant. So if we put this all together, for a linear pattern, what we see is that the change in y divided by the change in x should always be constant. And this little triangle symbol that you see is the Greek letter delta. It's the symbol for change. So again, what we see on screen is that the change in y divided by the change in x should always be constant. This is a ratio, a fraction, of the change in the dependent variable to the change in the independent variable. This becomes a little easier with some examples. Let's look at our change in our dependent variable. In every case, this y value, or the dependent variable of cost, increases by 20. At the same time, the x data, or the distance, the independent variable, is always increasing by 100. So if we think about this ratio, our change in the dependent variable y is 20. Divide that by the change in the independent variable, the x, of 100. And this does give us a constant. Every change ends up giving us a ratio of 0.2. This is a linear relation. Let's look at another example. Sometimes students feel a little bit confused if we don't see the same jumps happening in the table, but we can still check if the pattern is linear. Let's look for those changes first. From the first line of the table to the second line of the table, our ratio will be 20 divided by 100, which gives us 0.2. Now let's look at the next changes. The change in our dependent variable y this time was 40. The change in the independent variable x this time was 200. It turns out we get the exact same ratio. So even though the pattern wasn't necessarily as obvious, this is still a linear relation. And this ratio has a special name. We can call it the rate of change, especially when we're talking about word problems. The rate of change shows up as this ratio of the change in y divided by the change in x. So in this example, it's representing a cost divided by a distance. So when we think about the dollars divided by kilometers, that actual rate of change of 0.2 tells us that the cost is $0.2 or 20 cents for every 1 kilometer. We can also see rate of change on the graph. In this case, with our graph, we have some very clear coordinate points crossing grid lines. We can see the change in x from 0 to 100 or from 0 to 200. We can see our change in y. From these first 2 points, we're moving from 60 to 80. So from the graph, we can still see that our change in the y values is 20 and our change in the x values is 10. This is already labeled on the graph for us, and we can still find the rate of change. We should also notice that if we picked a few different points, for example this one and this one, just like that second table of values, we can still find the same rate of change. We can see a change in y values from the first point to the last point, moving from 60 to 140. That's a change of 80. And we can see moving from 0 all the way over to 400 is a change of 400. Our change in y divided by our change in x gives us that constant ratio. So we've seen that the rate of change can show up in a table of values as that constant ratio. It can show up in the graph also as the constant ratio. We can also see this show up in the equation. When we talk about an equation to model this particular situation, the equation is that the cost, the dependent variable, is equal to 0.2, there's our rate of change, multiplied by the distance, the independent variable. We'll talk about this other piece in just a moment. The important idea here is that the rate of change shows up right in front of that variable. We might also see this written as something like y equals 0.2x adding 60. Now let's talk about that 60. It represents our initial value. And the initial value shows up in our representations as the starting value. So at the very start, when the distance was 0, the cost was 60. Another way to think about this initial value is that it's the value of y when x is equal to 0. It's easy to see the initial value on the graph because the initial value is where that line or linear relation crosses the y-axis. So here is our initial value of 60. And just like the rate of change, the initial value can be represented in the table of values as that original value of y when x is 0. It can be represented on the graph where your line crosses the y-axis, and it shows up in the equation. When our equation is in a form where we have the dependent variable all by itself and equal to something else, the initial value is the number that doesn't have a variable beside it. We'll talk about other forms of equations later on, but for now, this idea of looking for the number all by itself is a pretty safe way to find the initial value. The last thing that we should talk about is deciding whether or not an equation or function is linear. This is sometimes easier if we start out looking at what is linear and what is not. This equation is linear. This one is not. I can tell because I'm going to have an x multiplying by an x, making an x squared. This equation isn't linear because I already see the x squared. This equation is linear. Even though we have brackets, we're not going to have any x squareds. So this still works out. This equation is not linear. Dividing by x means that it's not linear. Lastly, this equation, even though it's not in y equals form, is still linear. I see 2x, but not an x squared or dividing by x. And even though there are 4 y's, that still works too. So when we think about what makes an equation or a function linear, the big idea is that if we expand to get rid of the brackets, our expanded form will only have x to the power of positive 1. And remember that we probably won't see that exponent written, as well as a y to the power of positive 1, and we probably won't see that written. So x squareds, or dividing by x, which is the same thing as x to the power of -1, mean that the equation is not linear. Taking a quick look at all of these equations which are linear, let's practice finding some information. The rate of change is the number in front of x. So our first equation has a rate of change of 0.4. The second equation, the number in front of x, we're actually going to consider to be -1/2. Don't forget the negative. And then the next equation has a rate of change of 1.25. And lastly, -4.2. The initial value is the other piece, the +6, the 10, which is actually a +10, the -100, and the +87. A situation or a word problem will have a linear model if the situation involves some kind of pattern of adding. That pattern of adding is going to be related to our rate of change. If we talk about the amount of money in a bank account increasing by 10% of the balance each month, well, let's think about what that would look like. If we start with $1,000, 10% is $100, so at the end of the month we add $100 and get $1,100. And then at the end of that month, 10% is now $110, so the next bank account balance is $1,210. But wait a minute. We didn't add the same amount each month. That's not a constant rate of change. On the other hand, if we talk about a mechanic who's going to charge $65 for parts and then $40 per hour worked after 1 hour, the mechanic is charging $105, we're adding 40, and after another hour we add another 40, the mechanic charges $145, and after another hour adding another 40 for $185, that is a linear pattern. So let's wrap up. When we talk about linear relations, we're going to see a straight line pattern in the graph. We're going to see a pattern of adding in the table of values or the description, and most especially when we talk about the rate of change or the ratio, we're going to see that constant nature. Oh, and one last thing, grade 10s. You're going to have a short, simple surprise quiz on this material, so if you need to, watch the video again so that you feel comfortable.